In this lesson, we're going to take a look at the product rule for derivatives, another derivative rule that we can use to find derivatives of functions quickly. We'll begin by stating and proving, or really looking at a kind of geometric explanation of the product rule, and then we'll turn to some examples of its use. Let's begin by stating the rule and seeing why it works the way it does. We're turning now to some more complex derivative rules than the ones we've introduced up to this point. So especially when you think in terms of arithmetic combinations of functions, we have two derivative rules for those right now. We have the sum rule and the difference rule. And we can kind of state these together using the plus or minus symbol because they're so similar. They say that the derivative of the sum of u and v, or the difference of u and v, where u and v here are function variables, think of them as functions of x, the derivative of the sum or difference can be found by taking the derivative of each term and then adding or subtracting the derivatives. Use the same operation as you used to join the functions originally. So that's a very simple rule. If you can find the derivatives of the parts, it's easy then to put them together to get the derivative of the whole using the exact same operation, addition or subtraction. We're turning now to rules for multiplication, and then after that we'll look at division. And these are more complicated, and a sort of quick explanation of why that is to say that multiplication and division create a stronger bond between the functions that they join. And what ends up happening is that when you take the derivative of a product or a quotient, you need to account for how that operation causes the functions to interact. And the interaction is more complicated with multiplication and division than it is with addition or subtraction. Hence, the derivative formulas are more complicated. Let's state the product rule. This is the product rule for derivatives. This tells us how to find the derivative of a product of two functions. In other words, of two functions that are being multiplied together. Here's the formula. If we're taking the derivative with respect to x of u times v, again, u and v here are functions of x, then we find this by using what you see on the right, u times the derivative of v plus v times the derivative of u. So the big thing to note here is that we're not just finding the derivatives of u and v and multiplying those together. Again, the product rule is more complicated. The way it works is that we multiply each function that we're starting with by the derivative of the other one, and then we add the results of those products. If you want a kind of slogan that has a little bit of a rhythm to it that you can use to remember this, you can use this: first times derivative of second plus second times derivative of first, where the first refers to the function u and the second refers to the function v in the product u times v. To see why the product rule is true and why it works the way it does, it helps to look at a kind of geometric interpretation of it. We could do this analytically as well using the limit definition of a derivative, but it's not very illuminating. It can be done. It certainly needs to be done if we're going to give a completely rigorous introduction to calculus. But for the sake of understanding how to find derivatives of functions and why these formulas work the way they do, the analytical proof is not very illuminating. So we'll look at a geometric interpretation of it that helps to indicate how it is that multiplying two functions together creates a kind of close bond between the changes in those functions when we take the derivative. So to begin, think of u and v are two functions that we're multiplying together as representing sides, or really lengths of sides, of a red rectangle that you'll see in a diagram here. I'll zoom in on this. So for right now, just concentrate on the red rectangle whose width along the bottom is length u and whose height is length v. And now we're going to increase u by a little bit. We're going to increase it by an amount that we will call du. And we'll do the same thing with v. We'll increase it by dv. And you can see du and dv there on the bottom right and the top left. And when we increase the lengths of u and v by those amounts, you can see that the whole rectangle gets a little bit bigger. We add on some extra space, the blue chunk, the green chunk, and that tiny little yellow piece there. Keep in mind, by the way, that du and dv, what we sometimes call differentials, represent very small changes in the values of u or v. So even though in the diagram those look like relatively large changes, mentally you want to think of them as being very, very small. That's what we're dealing with when we're finding derivatives. Now notice that the green rectangle on the top has an area of u times dv. You can see that from the diagram. And the blue rectangle has an area of v times du. There's also the little yellow rectangle in the top right. And you can see here from the diagram that its area is du times dv. But keep in mind, du and dv are extremely small here. And so in practice, that is going to be a negligible amount of space. It will be so small when du and dv are small that we can actually ignore the yellow piece when we're looking at how the area of the entire rectangle has changed. So if we ask then, by how much has our rectangle's area changed, starting from the red rectangle and then expanding it by increasing u and v by those amounts, what we get is, in effect, the derivative of u times v. That's what a derivative tells us, how much something changes. And the amount of that change is u times dv, that's the area of the green rectangle, plus v times du, that's the area of the blue rectangle. Again, the yellow rectangle is so small that we can ignore it. And if we rewrite that using prime derivative notation instead of differential notation, this is what we get. The change in u times v is u times v prime plus v times u prime. In other words, it's u times the change in v plus v times the change in u. That's why the product rule works the way it does. And in effect, Leibniz figured out how to prove this by reasoning in much this way about the area of a rectangle. Let's turn now to look at a couple of examples in which we apply the product rule. The first example will involve finding the derivative of a product of polynomials. So we're going to find h prime of x, where h of x is what you see there, 3x minus 2x squared times 5 plus 4x. Notice that we're multiplying two polynomials together here. The first factor in the product is 3x minus 2x squared. The second one is 5 plus 4x. 5 plus 4x is a linear function, but linear functions are a special type of polynomial function. So to take the derivative, we'll apply the product rule. And this is what we get. We take the first function in our product, which is 3x minus 2x squared, and multiply it by the derivative of the second function. The derivative of the second function is 4. Keep in mind, 5 plus 4x is linear, so its derivative is just its constant slope. That's the first times derivative of second part of the product rule. And then we add the second function times the derivative of the first. The second function is 5 plus 4x, and the derivative of the first is 3 minus 4x. We can find that using some of our simpler derivative rules, like the constant multiple rule, the linear function rule, the difference rule, and the product rule. Sorry, the power rule, excuse me. And then after that, anything else that we might want to do at this point is just going to be algebraic simplification. If we distribute the 4 that you see there, and we multiply 5 plus 4x and 3 minus 4x using FOIL, this is what we get. And if we combine like terms and rearrange things so that the polynomial is in descending order, with the degree of the terms going down as we work from left to right, we end up with this, negative 24x squared plus 4x plus 15. That is the derivative of h, the function we started with. By the way, you don't have to use the product rule here. Sometimes you do have to use the product rule to find derivatives unless you want to use the limit definition. Here, there is another sort of algebraic way to do this. We could have multiplied the two functions that make up h first using FOIL, and then taking the derivative of the polynomial that we obtain. That wouldn't require the product rule. That would just use the techniques we've already introduced for finding derivatives of polynomial functions. But if you know the product rule, you might find that it's a little bit quicker than using that method involving FOIL and then taking the derivative. In any case, we would have gotten the same result. All of our derivative formulas and our algebraic principles agree with each other. They are what mathematicians call coherent or consistent. In other words, you're never going to get two different results for the same thing by applying two different methods. Let's take a look at one more example involving the product rule. And this will show that the product rule and the constant multiple rule agree with each other. We're going to find the derivative of 3 times the square root of x. And we're going to do this by using the product rule. Notice that what we're dealing with here is a product of 2 functions. The first one is the constantly 3 function, and the second one is the square root function. We already know the derivative of the square root function. We found this using the power rule in our lesson on that formula. We found that the derivative of the square root of x is 1 over 2 times the square root of x. So we'll use that in our example here. One thing this means, though, since we already know the derivative of the square root of x, we could find the derivative of 3 times the square root of x very quickly using the constant multiple rule. The derivative of 3 times the square root of x is just 3 times the derivative of the square root of x. That's an application of the constant multiple rule. And the derivative of the square root of x is 1 over 2 times the square root of x. So the result we get, if you simplify a bit, is 3 over 2 times the square root of x. That's probably the fastest way to find this derivative, given what we already know about the square root of x. But we're going to do a little bit of extra work here and use the product rule instead, just to see that we end up with the same result. And so then it doesn't matter which one we use. You can pick whichever method you find more straightforward or more interesting or simpler. So again, the key here is to note that our function that we're working with is a product, 3 times the square root of x. And both of those expressions can be thought of as defining functions, a constant function and the square root function. So when we take the derivative, we'll start with the first function, 3, times the derivative of the second one, which is the derivative of the square root of x. And then we'll add the second function, the square root of x, times the derivative of the first one. Well, we know what the derivative of the square root of x is. It's 1 over 2 times the square root of x. And the derivative of 3 is the derivative of a constant function, so it's equal to 0. That's our constant rule for derivatives in action. And again, if we simplify that second term there, the square root of x times 0 is 0. And so we end up with 3 over 2 times the square root of x. The same thing we got by using the constant multiple rule. And what this helps to show is that these 2 rules, which both involve multiplication in some way, agree with each other, which means you don't have to use the product rule if one of the factors in your product is a constant, although you can if you want.